Now.
Mhm.
So, hi everyone. Thanks for joining today's seminar series organized by the Empathic Computing Laboratory. I'm your host, Pai. Now, guest speaker for today is, let's get this right the first time, Anatole Lécuyer, who is currently a senior researcher and head of a hybrid research team at INRIA, France. So his current research interest includes VR, haptic interaction, 3D user interfaces, as well as brain-computer interfaces. The title of his talk is Combining BCI with Virtual and Augmented Reality, which is about the research path of BCI research, how BCI and VR can be combined for novel interactions and applications. So the talk will roughly be about an hour, and then later on we'll have a brief Q&A session. Without further ado, over to you, Anatole.
Yeah, thank you, Pai, for the introduction, and thanks everyone for having this little chat a bit before the presentation. It's always appreciated. And for those of you, I don't know, we can make a little survey. I don't know how many people have attended the workshop at ISMAR on mixed reality and brain-computer interfaces. Does anybody attend? Did anybody? Yeah, Mark, of course, you were speaking there. But if you haven't, or at least if you have, sorry, because a lot of this presentation is very similar to the one at that I did at ISMAR workshop. But if you have not attended, then it's perfect. You are going to discover these slides. But I have added few materials now and then for this morning. I'm counting on something like a 25, 30 minutes of presentation, and then after we can have indeed this round of questions. Because after 30 minutes of presentation, I assume that it's tiring for everybody, especially at this late time in Auckland. Okay, I think I should start. So I'm going to talk about the work that we have been developing in our lab at INRIA in France. So we are located here in France. Do you see my computer mouse? Yes, my mouse cursor.
Sorry,
Do
I
you
don't.
see it,
Oh,
Red?
there it is. Yes, we
Yes,
see it now.
Yeah. Okay, great.
on the map, yeah.
So great. So you see, this is a map of France. We are located on the west part of France, the far west. We are the Britons of France. It's a special region where people eat crepes and drink ciders. Not all the time, of course, but regularly. And in this lab, we have been working on virtual reality for a long time now. We are one of the pioneer labs in VR in France. The lab was founded in the 90s. And today it corresponds to the activity of a group of 35, 40 people that I am supervising or leading. And in the lab, we can count on a bit more than 100 people working on VR. I'm counting here postdocs, PhD students, and permanent researchers. So it's quite a lot of people working on this topic in France, highly concentrated in France at this lab. And INRIA is the French National Research Institute for Research in Computer Science and Control. So it's a public institute, and it's also associated here with other engineering schools, local engineering schools, and other academic labs like CNRS, University of Rennes 1, INSA, and ENS, which are engineering schools. So if you want to have a visit to our lab, you're welcome. It's a bit far from Auckland, of course. It's a bit closer to Germany for the people who are stuck in Germany right now, or in Barcelona. You have a direct flight from Barcelona. When I'm going sometimes for PhD defense at Mel Slater's lab, I can enjoy this very fast connection with Barcelona. And you can visit, for instance, if you come to our lab, this great facilities that I am now showing here in this video. It's a very large cave called Immersia. It's a 10-meter wide cave in which we can conduct a lot of experiments. And recently we have improved Immersia in order to integrate in this very large cave haptic systems, haptic force feedback devices. We have two 6 degrees of freedom force feedback devices now integrated inside this cave. So it's a very impressive setup, and we have some nice demo to to show you if you come to France. The topic, the research topic of the team is 3D interaction with virtual worlds using body and brain inputs. And our objective is twofold: improving immersion and the presence and the user experience inside the virtual world, and improving interaction, the performance when achieving some task in different scenarios. We have different applications and different context of usage, like medicine. We have lots of collaboration with the Rennes Hospital in France, for instance. With industry, we collaborate with Renault or Dassault, big automotive or aeronautics company in France. Construction, we work with Vinci, for instance, which is a big French construction company. Cultural heritage, it's an important axis of research in our lab, because we have lots of collaborations with historians, archaeologists in Brittany, for instance. Entertainment and arts, we collaborated with a video games company, or arts. We like to establish collaborations also with artists in France. And the first connection with brain-computer interface happened in our lab in 2003, 2004, where when I hired a postdoc named Marco Congedo. Maybe you heard of him if you are familiar with brain-computer interface. He's now quite famous in the field, and he's working in Grenoble in France. He's now a senior researcher at CNRS. And we started to work on BCI together, really from scratch, nearly, in 2003. We hired Fabien Lotte, who is also a renowned researcher now in BCI in France, for a PhD in 2004, 2005. And this is a video from our very first work with Fabien, where we reproduce a motor imagery scenario, imagining left or right hand movements, but here with visual feedback coming from virtual reality. And this was the first version of our Immersia room. It was a ME cylindrical screen in stereoscopic with this vintage EEG headset that it took us, I think 30 minutes, 45 minutes to install the EEG headset on the head of this poor participant here. We used a lot of gel. It was very messy, very complicated. Now it's a bit easier. But the result is here displayed. You could, in stereo, enjoy both virtual reality and immersion. I mean, at least a little of immersion, and mind-based control or brainwave-based control in this scenario. So in a bit more than 16 or 17 years of research on brain-computer interface, we have a bit refined our general objective in combining these two technologies. Our intention is to study human-computer interaction based on this combination of brain-computer interface and virtual reality technologies. And we have identified 4 different research axes. And if you want, we can discuss on these later. And I will show you some examples of results that we have obtained on these different research axes. But this enables to summarize a little bit the approach in Rennes. First, we can study neuromarkers using VR as a paradigm. It's a benchmark. We consider that virtual reality technologies can correspond to, can consist in a benchmark for studying neuromarkers and brain patterns. And also we try to see if neuromarkers can be elicited in VR compared to reality. And you'll see some examples a bit later on. Then we like to study the BCI user experience. You'll see some examples also later on. We want to characterize what makes special a BCI-based interaction, what is special with it, how the user feels with a headset on their head, what's the benefit, what are the potential disadvantages of interacting using the mind or using the brain in virtual reality. Then we work on HCI, and we like to design BCI-based interactive techniques and novel interaction schemes in virtual environments. And you'll see also some examples, for instance, mixing BCI with other techniques like gaze tracking, so mixing brain and gaze inputs, for instance, for selection techniques or interaction techniques. And we like to work on translational research and application of this combination of BCI and VR. And we like to develop novel immersive systems for different purposes like medicine, sports, entertainment, industry, and you'll see some examples also later on. Voila, that summarizes a bit the kind of research that we are developing in REN when we are recruiting, for instance, PhD students or postdocs. This is mainly to work on one of these topics. And overall, what we like to do is to combine complex technologies like EEG and also fMRI. You will see that we are testing different kinds of input and measurement techniques, 3D displays, of course, VR headset or projection screens, haptics technologies, because at Hybrid, I didn't elaborate on this earlier, but we have a lot of activity on haptics and haptic interaction too, and we like to combine this with BCI, gaze tracking, etc. And we conduct a lot of real-time and online experiments with participants, and compared to other people who are working or other researchers who are working on offline signal processing in BCI, our life is harder probably because you know that experiments with BCI can be a lot of trouble, and it rarely work the first time. So it's a lot of effort when you do real-time experiments with BCI and participants. Some salient projects in the team, and then I'll elaborate on research results. We started the first project on BCI in France. It was actually the first project on BCI in France overall at a national level, called OpenViBE 2005-2009, with a group of partners, industrial partners and academic labs and association dedicated to disabled people. Because this project was dedicated to handicap and to disabled people, and we wanted to test these technologies in the field of handicap, and we designed, for instance, systems enabling to communicate using brain waves. It's the speller that you see on the left here, the classical P3 speller, but that we redesigned, and we did several works on trying to improve the interface of the P3 speller. And on the right, it's some kind of basic video game that can be used by handicapped people to play a Jedi in the Star Wars movie, lifting the spaceship here using motor imagery of the legs, imaging feet movement to raise the virtual spaceship here. In this project, we designed this software called OpenViBE. I'd be happy to hear if some of you are using OpenViBE or not. Can we make a survey? Who is using OpenViBE? Who has been using OpenViBE? Okay, not very popular in Mark's lab, but I'll try to promote it.
I've been using it a little bit, yes. I think Ishan tried a little bit, and then we have Amit was playing a little bit with it one time.
Oh yeah, I've used it about a year and a half ago, quite a bit, and constructed quite a bit. Done a lot of work with the designer.
Okay, thanks.
Yeah.
Maybe later on we can discuss a little bit during the questions. You can tell me about your experience with it. Sure. OpenViBE was really designed something like 15 years ago when we identified that in the field there were not a lot of tools to start with this technology. And at least these tools that were existing were not very user-friendly. It was for programmers and people who just want to play around and connect these technologies with other technologies like BCI. It was very painful for them to start with. So we wanted to provide a tool to the community, to the research community, that could be hopefully more user-friendly and people could start earlier, and especially for disabled people, we wanted to promote this technology and make it more fastly spread around in the research and in the medical field. So we designed OpenViBE with this objective in mind. It took us 3-4 years to make the first release, and now we have reached the 30th release. So it's in October, last month, we released OpenViBE 3.0, and the success is there because we have a lot of downloads per year, around 6,000. It's used by a lot of people. The OpenViBE paper is used and cited in many publications. And it corresponds to 40 years of development, so 40 years of development total. So it's a lot of efforts, but we intend to continue to support this software. INRIA is supporting us. We could recruit a nearly permanent position for an engineer, and hopefully soon it will be a permanent position for an engineer working full-time on this project to sustain the software and make sure that it stays free and open source, a tool that can be used by the international community for developing and working on BCI. And if you look at examples of project based on OpenViBE, for instance, on YouTube, if you type OpenViBE, you'll see lots of different videos, such as this robot control based on brainwaves, or at the upper left here. At the bottom left, you see an artistic project designed with OpenViBE, and there are lots of studies in motor control or on neuroscience that are based also on OpenViBE, and we are very proud of this, and we hope that it will be continuing for the next years, and hopefully after also. Later on, so all our I think 100% of our papers are based on OpenViBE, everything that we are developing at INRIA in all the groups. Now there are around 5 groups working on BCI at INRIA in France, in different cities in France, in Grenoble, Bordeaux, and Sofia, and Paris, and Rennes. And all these groups are using OpenViBE, and we are developing our research on this software. So for instance, a bit later on, 2009, 2013, we launched another project working on video games based on brain-computer interfaces. I think this was also the first project on this topic, working with industrial partners. So we had Ubisoft, the famous game company, with us in this project to design different prototypes of brain-based video games. And you see here pictures of games that have been developed by video game studios in the project for demonstrating the potential of this technology in the video game field. And in our lab, we designed also prototypes of BCI-based video games in this project. You see here on the bottom left, and I hope that the videos are playing well. I hope that it's not too saccadic, and that it's okay, it's fluid. Maybe let me know, Pi, is it okay for the videos?
Yeah, it's perfectly fine.
Okay, thanks for the feedback. So here on the bottom left, well, hopefully you can see the flashes, and we are using SSVP. I hope that you are familiar with this notion too. This evoke potential in the visual cortex of the user. That's the reason why the electrodes are located at the bottom, at the rear of the head here. And we are using SSVP to control this spaceship and play this Space Invader-like video game using SSVP, and destroying the spaceships here coming at the top of the screen using 3 commands: shoot, go left, go right, corresponding to 3 different frequencies of flashing that are detected in the motor cortex, in the visual cortex. And we played around with the visual feedback in this project. So we tried different kinds of visual feedback for the SSVP. And if you want, we can discuss about this later. And on the bottom right, I'll stop this video and activate the other one. I hope you can see here this sequence of 2-user motor imagery. It was one of the first time that we are connecting 2 brains to a video game here. So it's a mental duel. It's a mental fight between two brains, and here it's motor imagery, left or right hand motor imagery, to send the ball to the right or to the left of the screen and to score goals. And what is interesting in this paper is that we tested different approaches. We tested the collaborative way versus the competitive way. So in some cases, the two people were fighting against the computer somehow in a collaborative way. And in some other condition, they were fighting one against the other. So we were trying to see if, and in the third condition, they were alone, meaning that the second user was not here. So we were comparing being alone, being two users, one against the other or one with the other, to test the motivation and see the impact on the performance of the BCI. And what was funny is that we saw an effect. We saw that for some participants, being two people in the same situation with this headset on, could increase the BCI performance and could increase the motivation. And so it gives some ideas for increasing the performance, not only using more efficient signal processing techniques, but also more engaging situations. So now I plan to show you some a set of examples and research results that we have obtained in our lab. I'll give you a broad overview of a lot of papers that we have published in our lab. Of course, not all of them, but a selection of these. And if you're interested, I can, after that, go into the details of one or the other, up to your preference. So to illustrate the first axis of research, so if you remember, I talked about trying to better characterize the neuromarkers in VR. In this first axis of research related to neuromarkers, here is one example. It's a paper that we published at IEEE VR in 2018. Maybe you know this one. We studied the neuromarkers of virtual embodiment and the agency toward a virtual avatar in virtual reality. And we wanted to see if there are some neuromarkers in the brain which can correspond to a good or a bad virtual embodiment. And to this purpose, we proposed this very innovative setup where you could be embodied in a virtual avatar. Here, you see the first person view in this video on the left, and you have to do some movement with your hands. And in some cases, the movements of the avatar are completely distorted. You can, for instance, introduce a lag, an artificial lag, or you can generate some issues with the animation of the hands, so that when you move one finger in the real world, it's another finger which is moving in the virtual world. And you can create these very uncanny and strange situations where your body is reacting very differently. Your virtual body is reacting differently. And what is interesting is that we indeed notice some neuromarkers, some brain patterns which are activated in your brain in these conditions. For instance, here on the right of the screen, you see this activity occurring in your brain. I will not enter into details here, but we have observed some modification in some power spectral density in your brain, which activate when there is a distortion of your virtual body animation. And what is interesting in this paper, notably, is that if you look at this brain pattern, it's the same that is activating in the brain of schizophrenic patients when they are facing an hallucination, a sensory hallucination. And it's very similar, suggesting that what you are experiencing when your virtual body is distorted in VR is close to the experience of a sensory hallucination. And it's also correspond to a loss of agency, the impression that you are losing the control of your body, which is also what schizophrenic patients are saying and telling about this experience of hallucination. Another example of using VR to study neuromarkers or to test the detection of neuromarkers in VR is this quite recent paper published at IEEE VR 2020, and it obtained the Best Paper Award last year at the conference. It's a collaboration with the Technical University of Graz, the group of historically of Putscheller and Gernot Müller-Putz right now, and with Reinhold Scherer. And here we wanted to check if error potentials can be detected in VR or augmented reality in order later on to use them, to exploit them. If we know when there is an error potential occurring in the brain of the user, maybe we can correct or propose some alternative solutions to the user to assist and to help him or her during the task. And here we concentrated our efforts on tracking issues. So imagine in AR or in VR that you are facing a tracking problem. We want to see if this is generating or not an error potential in the brain of the user. And we tested different kind of errors, tracking errors, error in the background, like a problem of bad positioning of an object in the background, or also a feedback error. And we noticed that some errors could well be detected in the brain, especially we tested the possibility to detect them in single trials, so classification in real time. And we obtained some pretty good results with the tracking errors. And in the end, what we've shown in this paper is that in VR and probably in AR, it's possible to detect error potential nearly in single trial. And later on, it can be interesting to have this information to propose some corrective solutions, for instance. And this is the last paper on this topic of neuromarkers. It's to show the kind of application that we can have also. It's a collaboration with a sport lab and also with EPFL, the team of José Milan at EPFL, with whom we studied the use of VR, of this great facilities that we have in Rennes, this cave that we have in Rennes, to study neuromarkers of athletes, of sportsmen or women in very safe and controlled conditions. And this is an example of a scenario of an Olympic sport. It's the 10-meter pistol, the 10-meter shotgun. I don't know exactly the name in English, but in this scenario, you are training to this 10-meter pistol on this 10-meter pistol stage. And in some cases, you are completely alone, which corresponds to the classical standard training situation in the real world. And in another condition, you are facing virtual opponents and a virtual audience, which is shouting in your back, which is generating a lot of pressure and anxiety. And what is interesting is that we could compare these two situations and try to see what are the neuromarkers in the brain of the user, which corresponds to the good shooting and to the bad shooting. And in order to anticipate when the shooter is going to well succeed and when the shooter is going to fail. And this can be used later on for neurofeedback approaches or for proposing other and novel kinds of training procedure. So if you're interested, we have a couple of papers on this topic. The second research axis that I was talking about is the BCI user experience. So I can mention here two works that we have done on this topic, which are quite fun because the first one, for instance, was we investigated the frustration of BCI user. So we wanted to see at which level of performance, meaning bad performance, you are going to stop using the BCI and put the headset away and break the headset. And we did quite a funny experiment because we did an experiment where it was a SSVP task. You had to select among 3 targets, 1 target. But actually, the headset was not connected to the task, meaning that whatever the performance of the user, the selection was completely artificial and computer-based. So the headset was disconnected from the task, and your brain actually was completely disconnected from the task. And whatever you were doing, the performance of the BCI was completely controlled. And so it was. We didn't tell that to the participant, of course, beforehand. Huh? We told them at the end of the experiment. And you see, what was interesting is that the frustration of the BCI user was quite low. We were quite surprised because the people were, even with a BCI which was failing. You see here on this figure, on this plot on the top right, that even though the error rate was quite high, 35%, meaning that the BCI was failing 35% of the time. Even in this situation, people would express a frustration, an instant frustration, quite low, around a 2.5 here on the scale from 1 to 7. So the frustration of BCI user, at least in control experiment, is quite low. It's good to know for you when you are doing a BCI experiments. Your BCI user are quite sympathetic with you during the experiment. And another experiment dealing with the BCI user experience was a paper published in CHI in 2017, where we studied the cognitive load. We wanted to see and to test if the participant of our experiment or the user of BCI could do something else with their brain, whereas achieving the BCI task. So can you do a secondary task, a secondary mental task, at the same time of using the BCI? Can you do something else? Can you think of something else? Or is your brain completely dedicated, must be completely dedicated to the task? So we did this experiment. It was, again, an SSVP paradigm. But at the same time, you had to select a target out of 3 targets on the screen. You had to do a secondary task, which was an end-back task. It's a memory task. I will not enter into the details. Some of you are probably familiar with the end-back task. We can discuss about this later on if you want. But what we showed in this paper is that when doing the SSVP paradigm, you can actually be very good at this end-back task and still succeed at the SSVP task at the same time. So it's here again, it's also quite positive, meaning that yes, you can think of something else when doing the SSVP task. So maybe it's different for other BCI paradigms, especially for motor imagery, for instance, or for other maybe more complex or endogenous brain activity. But in the case of the SSVP, it was quite promising. The third axis I was talking about is BCI-based interaction techniques, if you remember well. So here is an example of the kind of interaction techniques that we try to develop in our lab based on BCI. We studied the combination of gaze and EEG inputs for selection purpose. So you have to select the targets, and we wanted to compare the use of the BCI for target selection versus gaze tracking alone, and more interesting maybe, gaze plus EEG inputs, using here, it's depicted on the little diagram at the bottom of the screen, using a probabilistic approach and a fusion approach, combining the inputs of the gaze tracking detection and of the BCI-based detection of the target. And using a fusion approach and probabilistic models, we wanted to see if gaze plus EEG performs better than gaze alone or EEG alone. And the results are quite contrasted. Considering the current state of technology, we found that the BCI alone was really less performing than the gaze, and even the gaze plus EEG was actually not more significantly more efficient than the gaze alone. So still promoting the use of alternative technologies like gaze tracking, if you have to propose an accessibility technology which must be very precise in the case of the patients having still the capacity to use their eyes, of course. And on another aspect, it's the design of 3D user interfaces. We, in 2019 and 20, we tried to see also how to design effective 3D user interfaces for BCI in augmented reality. If I'm correct, this is also one of the first combination of brain-computer interface with a Microsoft HoloLens. And in this case, again, with the SSVP approach, with those flashing targets, the use case consists in trying to move these mobile robots. You see the trajectory. Maybe you can see my mouse cursor here. You have to follow this path and reach those little white targets on the ground here. And this is the first person view through the HoloLens of the user. You see these 3 flashing targets here, one for moving forward, one for turning right, one for turning left. And you can activate these commands by looking at the corresponding targets. And in this paper, we designed and we studied different kinds of 3D user interfaces for these flashing targets. So meaning that we changed the layout for displaying these targets using different kind of approaches, like sticking these targets to the robots, using different kind of planes. And if you're interested, you can check. We had like 30 or 40 different ways of displaying the targets, and we proposed a methodology for designing the 3D user interface for controlling the robots in this case. And so here what is interesting here is that it's really a general approach for showing a systematic way to design 3D user interface for a specific task here of robot control in AR. And it was interesting that we did, I think, like 4 or 5 studies in this paper for helping in designing those 3D user interfaces. And in the application context, you can see the follow-up study here, designed by Hakim Si Mohamed, who is now assistant professor at University of Lille, who later on, after this nice work on 3D user interfaces, tried to apply this to a use case of controlling a smart home environment. So here it's a proof of concept that you see in this video of 3 connected objects, a fan, a lamp, and a television, which are controlled using augmented reality, Microsoft HoloLens also. So it's the video which was recorded by means of the HoloLens here that you're seeing from a first-person view. And you see again those flashing targets, and you have contextual menus, meaning that the targets are flashing depending on the object which is located in the field of view of the user. So here you only see the fan, meaning that the other targets are switched off, and here you see all the targets flashing because you see all the objects. And you can select the different objects, and then after you enter into a tree of decision for after displaying the different targets and selecting the different items corresponding to the object that you are actively controlling using your again your brain-computer interface and the SSVP approach. In a different context, and trying to combine BCI with other technologies, here we wanted to couple BCI and haptics. We did several studies on this topic, and this one is probably the most teasing one. It was the first that we published in 2012 on combining brain-computer interface and haptics. Here, the idea was to benefit from haptic guidance when the workload was high. So it's a different BCI that we are using here compared to the previous ones that I've shown. Here it's a BCI which is extracting the mental workload. And when the mental workload is detected to be high, we activate haptic guidance, a force feedback, which is helping to slide along the walls of this maze here. You see the result of the classification of the mental workload here. It's quite difficult to see it. It's the cursor that the person is moving, this little dot here, becomes blue when the workload is high. So you see that the workload remains quite high in this part of the maze here. And then the force feedback here is activated to help the user, because he's very concentrated on this part of the maze. It stays blue. And when now it starts to become white, meaning that the mental workload is is low. And so we don't activate the force feedback here. Okay? Voilà. And in straight line, after this after this result, we design also a proof of concept. It's a very basic proof of concept, of course. It has not been studied and in more details, but it was just for illustration purpose. We didn't use or call for medical doctors to use it because it was a medical simulator, a proof of concept of medical simulator for training surgeons to biopsy and the detection of tumor in the liver. We propose this proof of concept, which is based on brain-computer interface and haptics. And it's a training system which activates automatically guidance and assistances, aids, visual aids and haptic aids when there is a high mental workload detected by the BCI at the level of the EEG of the trainee. So it was quite an inspiring setup for showing the use of both brain-computer interface, haptics, VR in the field of VR training. To go one step further in the integration of BCI and augmented reality, let me show you a different category of works that we have studied in our group. This is in the field of brain activity visualization. We have published notably the mind mirror, and later on we published also the mind window in another setup. I haven't the video here displayed, but I could show you later. But here it's the example of the mind mirror. It was in 2013 or 14. HoloLens were not there yet. But the Kinect was quite popular at this time, and we use a Kinect together with a BCI and a visual display here to display the brain activity in real time in a mirror mode, meaning that you are looking at yourself here in this somehow a teleconf-like system, and you can see your brain in action in your brain, in your head. So you can display brain activity, for instance, beta activity or alpha activity in real time. And you can select the channel, by the way. It's like a television. You can activate the channel of your brain that you want to look at in the mirror. And you can see your own brain in your head in action. And you can try to try some strategies for controlling your brain. And this can be interesting for neurofeedback systems and neurofeedback therapies, where you need to find ways to control again your brain and recover some brain control and change some of your brain activities for in some specific therapies. And I will come back to this in a minute. And the system was published like 6 or 7 years ago, but we have continued to work on different kinds of feedbacks and VR uses for displaying brain activity for neurofeedback approach. So I don't know if you're familiar with neurofeedback, probably, hopefully yes. maybe you can tell me, Pai, are you familiar with the neurofeedback in your lab? The concept of neurofeedback?
I don't think we explored too much on neurofeedback. Do you mean like some sort of an output instead of input for using BCI?
But, well, it's the general principle which consists in observing that if you have a feedback about your brain activity,
it's like a loop.
Yeah, if you have a closed loop, then you can progressively learn to control this brain activity pattern.
Oh yes, there's some research about that. Yeah.
Voilà. This has been observed like in the 1970s already, and by showing a gauge, a visual gauge, which is going up or down, connecting with, for instance, one of your frequency, your mu rhythm or your beta rhythm, then you learn progressively how to control your beta or mu rhythm. So this very general principle, which is the basis also of the learning of brain-computer interfaces, can be applied to different kinds of medical applications, especially for learning and better learning to control your attention for children with attentional deficit. I don't know if you're familiar with this kind of approach, but neurofeedback has been tested in a lot of different contexts for different pathologies, like attention deficit or stroke rehabilitation. So after a stroke, a patient can try to reactivate their motor cortex using neurofeedback. And the mind mirror I was presenting earlier on can be a tool for supporting those therapies. And here in this slide, you see another tool that we designed not in our lab, but in a startup company called Mencia Technologies that existed between 2013 and 2019. It has been brought later on by another company called Cerebro Technologies. And but the product that we designed, that Mencia designed, was based on our technology, on OpenViBE. And it was designed for helping children with attention deficit to recover attention and recover concentration and help them, especially children who are suffering from these pathologies, can be in a lot of troubles at school and can be really impairing. It can really impair their learning. So in this startup company, we propose a tool which is based on a tablet and a very simplistic headset for supporting this rehabilitation of the brain attention levels. And it was quite, it's quite promising. We should have the result of the clinical evaluations coming soon, actually, about this technology. And still working on neurofeedback for therapies, brain rehabilitation, neurorehabilitation, and brain therapy. We have launched a very ambitious project in France called Hemisphere, which is now combining EEG and fMRI, the fMRI scanner, so another source of inputs about brain activity in order to strengthen the therapies of the brain. And this is for stroke patients and also for depressive patients. We have 2 different clinical studies currently ongoing at Rennes Hospital. And this is a video of the setup that was developed in Rennes tested with both healthy patients and healthy participants and also patients. First, the participant is equipped with a 64-channel EEG compatible with the fMRI. Then they enter the fMRI scanner. And after that, using both EEG and fMRI, they have to control a virtual ball here and lift this virtual ball based on their brain activity. And to do so, they can control, and I'm going to activate the second video here, to lift the virtual ball here. They have here, in this scenario, to increase their EEG level of activity and also their fMRI level of activity in the motor cortex. If they succeed in raising their EEG activity corresponding to the motor cortex, then I'll try to launch again this video. There you go. It corresponds to the right axis. And if they can increase the motor cortex activity as measured by the fMRI, it is increasing here the other coordinate of the ball on the left axis, meaning that if they succeed in increasing the activity in both fMRI and EEG, then they can reach this blue region, which is the final target, corresponding to the best activation of the brain region as measured by both fMRI and EEG. So I hope this was clear. You can see the results, the first results with the healthy participants depicted on the fMRI images at the bottom of the slide. And what is interesting here is that you see that when using EEG alone, it's in green here, you activate the motor regions. Using the fMRI input alone, it was one of the conditions in this experiment. You also activate a bit broader regions. And when you use the two conditions, the two feedback at the same time and the two measurements techniques at the same time, fMRI plus EEG, the activation of the brain is much broader. So it's very promising for using multimodal imagery techniques and combining both EEG with other measurements like FNIRS or fMRI in the field of BCI and neurofeedback. So this is we are reaching the end of my talk, and as a conclusion and as a projection toward the next steps, I could say a word about this future of combining VR and BCI, and maybe the next step consists in designing native hybrid technologies, integrating a lot of sensors in the VR headset, for instance, or in VR systems, integrating both VR technologies and neuroimagery techniques and methods. You see an example here, which you probably already know. It's the Neurable headset combining dry electrodes together with a VR headset, and illustrated here in a P300 based selection of virtual objects, selecting the objects using only the attention of the participants as measured by the electrodes of the headset. And as illustrated in this talk, I think there is a lot of applications for this combination and these hybrid technologies in the field of health, sport, training, education, games. And that was also the purpose of this presentation. It was to show you a lot of different examples of mixed VR/EEG setups for different application purposes. Voila, and to finish with, I'll show this video of, it was one of the most one of the cooler projects that we had in the team. It was an intern project, super fun, where we reproduced in our immersia room, scale 1, the sequence from the Star Wars movie on Dagobah planet. For the people who are familiar with the Star Wars movies, it's the Dagobah sequence where Luke is trying to lift the X-wing swamped in the swamps of Dagobah, trained by the Master Yoda. And here we are using a wireless headset, EEG headset, motion tracking, specialized sound, 3D graphics, dating from 2013, but it was a lot of fun. You had to train to become a Jedi Master. And just for you to know, the Force is not really with me because I'm not a super good Jedi Knight. I'm still an apprentice of the Force. But I'm trying to do my best, and I'm trying hard on it. And maybe later I'll be better. Voilà, this concludes my talk. Thank you for listening and staying late in Auckland, and I'll be happy to try to answer to your questions if there are.
Thank you very much for the very interesting presentation, Anatole. So I'm sure there's going to be a lot of questions because a lot of students in the lab are actually working on combination of BCI and AR/VR research actually. So we're now open to questions, and if there are any, please raise your hand in the participant list and I'll call you out. Either that or you could just type it down on the chat and I'll just read out the questions. Is there anybody? Ishan, I see that you have your arm raised the whole time actually. So do you have a question or?
Alireza can go first because the kid is waking up. Sorry.
Oh, okay, yeah, no worries. So Alireza would like to go first.
Yes, thank you, Anatole, for the presentation. It was really good. Actually, my question, I wrote, actually I have a lot of questions, but I just, summarize them. So the first question is this, when you talk in the first of your presentation about using EEG for identifying hand movements for motor imagery parts in the brain. So did you use another input for your model or not? Or just you use EEG?
Yeah, it was. Thank you for the question, and thanks for starting, because it's not always easy to start asking questions. So thank you, Alireza, for that. No, we basically, in all our setups, I think based on motor imagery, in most of them, we only used EEG signals and very classical approaches, the Graz BCI, if you're familiar with this very standard pipelines that was designed by Graz. So we mainly use EEG. In some cases, we used EEG to extract motor imagery, but we also use motor activity for a different purpose. So for instance, we designed video games where you could play with your hands and also with your brains, and it could be one or the other or the two at the same time. So, but it was not exactly extracting other patterns for maybe helping the motor imagery detection, if that was what you were mentioning.
Yes. Another thing is about the features that you extracted from the EEG. Those features that you extracted to understand the brain during the task, it was handcrafted features, or you use some AI models to extracted features automatically to finally build your model.
Was it for the virtual embodiment Neuromarkers study,
Yeah.
or it was for another study?
No, it was, I think, for Neuromarkers.
For this one?
Yes.
Yeah, for this one, I think we didn't use, so to speak, AI model to really well identify automatically somehow the neuromarkers. We had some priors, we had a priori. Especially, we look at different brain PSD, power spectral density. We look at different frequencies, and we exhibited some statistical difference in some of these frequencies that we are somehow
so it was
expecting.
Handcrafted.
Yeah, it was handcrafted mostly.
Oh, okay.
Of course, we use the statistical analysis to gain and to identify those neuromarkers that are statistically and significantly different from one condition to the other, but it was manually crafted, yeah.
Mm-hmm. And in terms of using fMRI and alongside with EEG for motor imagery part, normally one of the artifacts in fMRI is movements. So it's destructive feature in the fMRI. So how did you deal with that? Using fMRI and EEG is reasonable because they both give spatial and temporal information to your data, total data. So how did you deal with real movements and those artifacts that comes from those movements in fMRI?
Yeah, it's a very good point too. It was a challenge indeed. So we use tools, not necessarily tools that we developed, but tools provided by the manufacturers who was proposing the EEG headset, which is compatible with the fMRI scanner. So they propose software tools for automatic detection and correction of some of these artifacts. Then we had a camera recording the participants, and we were trying to detect, but it was manually also, or let's say visually. We were visually detecting when the participant was moving or not, and we are really instructing the participants to remain as much as possible to stand and not to move. And then after the task, we had a lot of work on trying to, here again, using artifact detection method on EEG, for instance, to really to carefully try to identify the trials in which there were some problems and issues with the signals. But it was of also manually editing work.
And the questions, sorry if it's too long. So, you know, my research is about using EEG and FNIRS together to measure emotional state of the brain to finally, you know, make a more realistic and immersive experience of AR using AR/VR headset. The question that you mentioned about the brain patterns, identifying some brain patterns. Did you, in terms of not using fMRI, just EEG part, did you notice any specific pattern related to the brain phase using EEG, or you just focus on the, you know, amplitude of the, you know, potentials in the cortex?
It really depends on the. So I'm not the specialist of the band or of the crew on the neuromarkers, and I rely on other colleagues who are more experts in neuroscience. So I'm maybe not the best to qualify to answer to your question, but we have tested in the team a lot of different approaches for for brain features on EEG. We tested a lot of different paradigms, so it's difficult to answer to your question in a very specific way. We tried a lot of different brain paradigms like SSVP, motor imagery, P300, error potentials, or investigating a lot of different neuromarkers for different purposes. So it was really case dependent. So it's hard to answer to your question like this. And we tested a lot of different signal processing approaches and feature extraction methods. So I don't have one recommendation on this. On on the detection of emotion, it's quite controversial. So good luck with that, because there are lots of papers a bit over-claiming or overstating on this. So, but it's also a great challenge. And maybe by combining these two techniques and two measurements methods, you have better chances to propose nice results on this. So I would just advise to be careful with what you are claiming on this topic, because you will be weighted on this topic of emotions.
Thank you for the answers.
You're welcome. Sorry if I was not very clear on this last one.
No,
I'm
it's
not
okay.
super expert.
Thank you. Thank you.
All right, let's keep the questions flowing. Is there anybody else?
Can I ask one question, Pai?
Yes, please, Ishan.
Sure.
Yes, Anatole, thank you very much for you know, sharing all the research that Indria has done. I just want to ask, because I think maybe around 5 years ago, I had an experience like a trying P300 speller in a Radboud University, and but you know, most of the time people who use this, they use only like one direction, so only one person's they interacted with monitors, so they can use their attentions to spell one word or a letter or number. I'm just wondering, have you tested, like, for example, when two people, like, they are in VR, for example, they are trying to spell a number or letters, but you measure like the activity of the two brains of these people, where they communicated either through AR or VR. So probably it will make a better like indicator to what extent, you know, they can collaborate in this situation. I'm just wondering, maybe you have an experience?
Well, thank you for the question, Ishan. We had a lot of discussions about hyper scanning and mixing the brain activity of two people for maybe trying to increase the detection. I don't remember if we went very far on this, because it was with one student who left the lab now several years ago. But I remember that this is something really that that is a super interesting path. So I would encourage indeed in trying to investigate on this one. I think in our Brain Arena paper in 2013, where we talked about these two brains connected to the video game. If you know this paper, I think
I think I read that one.
Yeah, I think in this paper we talked about the different schemes, mixing schemes, at which level you can go up to the EEG, at the EEG level, then at the classification level or the classifier level, then at the interaction level. So we envision at this time different schemes, but we didn't have time to explore all these schemes. So yes, I suppose that there are lots of stuff you can do with hyperscanning. It's super trendy at this moment. So, but a lot of stuff are very trendy in the BCI field. So it's, I'm sure that it's like always, you can find your path. But we stopped after Brain Arena, I think, on this topic. But I suppose it's very promising. So I would encourage to investigate this again.
All right. Thank you. Maybe we can have a discussions later about this. Maybe in one of your teams do the same thing, like what we're doing
at
here.
This moment, I don't think we are investigating hyperscanning, so it's not something that we're working on. But it's but clearly it's on your list in Mark's lab.
Mm-hmm. Yeah. Thank you.
Thank you.
Yes, Prashant, you have a question? Sorry, Prashant, I think you're still muted.
Thanks, Mike. So that was a great talk, Anatole. Thank you so much for sharing the amazing research. So my question is, so before I go into my question, I'll give a bit of background about my research. So I'm doing research in remote collaboration and mainly using AR and VR for remote collaboration. And on the next stage of my research, I'm trying to use more physiological sensors to get meaning and share the meaning out of in the collaboration setting. So I'm looking at a couple of devices like Luxit, Empatica, Shimmer, and Microsoft Band. And I was also quite interested in the new upcoming Galileo from OpenBCI. So can you describe a bit about that, the new headset that is coming towards mixed reality?
I'm not super familiar with it, so sorry. I will not be able to comment a lot on this. Sorry for that. But okay. I just want to share with you a sentence that we got from an expert in BCI, in HCI, because what was funny is that a couple of years ago when we were presenting BCI at INRIA in our lab, the people from the HCI field were very reluctant in this technology, and they have lots of, they are super conservative with this technology because they don't see the meaning of this one with respect to other accessibility technologies, which are much more reliable, for instance. So it's sometimes very difficult to pass, but you know that probably papers at CAI for this reason. And I remember that somebody told me, but it was very funny, when you put two weak signals you obtain together, you rarely have nothing more than another weak signal. so you have to be careful when you mix physiological computing and EEG data together, that in the end it will maybe not make your life better. So you have to be very careful with that and see how you mix these two signals and what are you extracting from one and the other. How do you think that they can be complementary? And I remember that this was the case, for instance, with the gaze and BCI study. We were super optimistic about this. And the results were really crappy. I mean, we were really expecting that BCI plus brain, BCI plus gaze would increase at least, would behave the same at least with respect to gaze, but it was very disappointing in the end. So good luck with this mixing of physiological data. It's a lot of hard work, but in the end, I'm pretty sure that it's a good path. But you really need to be careful. But it's clearly interesting, and it's the future. So good luck with that.
Thanks.
Okay, I think maybe we have time for one last question before we call it a day.
I had a question, Anatole,
Yes,
and this is a short one. You just mentioned before that the gaze and EEG did not work well together, so the EEG did not provide any benefit from just using the gaze. Can you explain a bit more why you think that is? Is it because the gaze already was so good for the task, or was there just no some performance for the EEG that produced worse results?
Yeah, I don't remember in all the details of this paper, so I should look at it maybe more carefully. What was just for the fun of it, I remember that this PhD, this Evan Andeol, he was really a bright PhD student, and he did some great work during this entire PhD. But I remember that in the end, I think we realized that he made a PhD with the highest number of non-significant results. It was non-significant result all the time, all these studies. But what is quite positive here, I mean, we had good hypotheses like this one that you see, Mark. We had the same. We said, wow, it should work, right? We put gaze plus EG, it should increase the system. But in the end, we paid a lot of attention in our setup, in our data analysis, in our signal processing methods. We were recruiting good people to help up on all these aspects, and non-significant result. But in the end, the good news is that, yes, you can publish papers with non-significant results, and it's possible in the community. Of course, it's not always the case, but we even succeed in making a Chi paper with non-significant results. So it's still possible. And when going back to your question, Mark, I'm not sure. I don't want to say stupid things here because it's already old in my mind. I should go back to the paper and the interpretation, but I'm not sure we had a proper interpretation here. It was just that, yeah, probably it was a bit of everything. The gaze is already quite efficient. The noise in the data is probably and especially across the participants, is probably also another source of problems in our probabilistic approach and fusion model. So that there were a lot of different factors that could explain this probably. But the good news is, yes, you can publish non-significant results. We showed it.
Okay, that's great. Thank you.
Yeah, I think Kunal, you had one question, so maybe let's just fit in one last one and we'll call it a day then.
Sure.
Yeah. Thanks for the insightful presentation, Anatole. I mean, I have attended the ISMAR one as well, but there are few new things. Yeah. So my question is again about the same study that Mark and you mentioned about, like BCI interaction with robot control in AR, where you are using gaze and EEG. So I could see like you used gaze. I mean, from the video, I could see like you used gaze to move the robot forward, left and right. But like if you can maybe give like a glimpse on how did you use the EEG data in, like what kind of interaction was it, improving the eye gaze interaction, or like how was the EEG data being used in that particular study?
So sorry, I was probably not clear enough, but in this robot control, we only use EEG in this case. The EEG and gaze was used in another study where we had to select a lot of targets, and especially in a dense region of targets. But for the one on robot control, we only used EEG data, and we used the SSVP approach, meaning that we concentrate our efforts on the extraction of the evoked potential of the SSVP at the back of the head. So maybe I was not clear enough in this case.
Oh, okay.
And in the robot control, it's a nice paper. This one, it's a TVCG paper and published last year for the robot control, and we really try to see different strategies of layout of targets. And we use both subjective approach and really BCI tasks with classification, accuracy, detection, and identification to assess the 3D user interfaces that we were developing. So it's another paper than the one based on gaze. We published only one paper on gaze plus BCI. It was quite negative in the end, so we didn't follow up on this one.
Okay, thank you very much.
Thank you.
Okay, so this should be the end of it. So thank you very much again for the presentation and insights, Anatole, as well as all the participants who joined today. I hope everyone learned something from Anatole in this presentation. I especially like the part where you mentioned that it could still be published without significance, because that I'm sure that will be very useful for the near future, actually. So
it's not easy, huh? It's not easy, but you can do it.
Yeah. That's very hopeful. All right. Okay. Yeah.
Well, what is really awful, I mean, with BCI experiments and especially when you're starting, it's very complex, because you make an experiment, it doesn't work. And it's really disappointing. And you don't know why, because it's coming from a lot of different potential sources. And it can be very frustrating, BCI experiments.
Yeah.
So good luck, guys and girls. It's a lot of there's a lot of frustration, but it's a very teasing topic, and it's a fascinating topic for the young people, for the older people. It's also a great topic.
I have a quick question before. Is it okay? Like just a small
well, since
question.
you mentioned it, yeah, let's do it.
Sorry. So Anatole, you said I mean, your lab has worked a lot on the memory, on the cognitive load perspective. So did you try to investigate the EEG, any correlation with EEG and skin conductance? Because skin conductance has been like a proven sort of like a cognitive load physiological signal. So if any
I'm trying to remember, I think we published a paper on this. I mean, the first paper on workload from Laurent Georges, you can check Laurent Georges. It was an EMBC paper, 2010, maybe or 11. I don't remember exactly. I think we investigated different sensors, but I'm not sure there were skin conductance in it on mental workload. So you can check. Recently, with Tiffany Luong at ISMAR, we did a lot with skin conductance and mental workload, and also, but it was without EEG. So you can check this other work on physiological computing in VR. Her work is really great. Tiffany Luong, ISMAR and VR, or maybe only VR, I don't remember, but Tiffany Luong, Luong, and this is mostly on mental workload and different physiological sensing, together with deep learning approaches. So if you want to check this, it's maybe very related. And with EEG compared to skin conductance, I'm not sure. I think Laurent Georges, we did some work on it. But our approach on mental workload was really based on training and learning. So it was supervised approach. Huh? It was not open loop approaches. It was you were doing one task with high or low mental workload, and you had a classifier learning to detect between those different activities. So it was a supervised approach on mental workload.
Got it.
That's
So
the basis for our work
class.
on. So it's a bit different from what, for instance, others are doing.
Okay, thank you very much.
You're welcome.
All right. So if there are any further questions, then feel free to drop a message to Anatole or through me as well. I can link you up. Also, Anatole, is there any possibility of internship applications? Just wondering.
Oh yes, sure. Or exchanges or visits. Yes, that would be great. You're welcome to visit, and we can discuss with Mark maybe later on also about this. But we would be happy to welcome you in our lab and then to work on collaborative project. I think we have submitted a project with Mark. I mean, Mark has written 100% of it. I didn't do a lot about putting my CV in the document, but I don't know if it passed, but if it was accepted.
We found out just a few weeks ago it was not successful, but I think we're gonna retry and do it again for next year. So we got some good feedback, and so I was going to talk to you about it later, but yeah, unfortunately it was not successful for this year. But we had some good feedback, and they basically encouraged us to apply for next year. So
okay, so I hope there will be some opportunities also coming, but it will be a pleasure, of course.
Great. Okay. So thanks again, Anatole, as well as everyone here, and we will see you guys in the next seminar. I'll end the recording right now.